Okay, good evening, everybody. Thank you for coming. I'm Petros Koumoutsakos, and together with Giacomo Indiveri, we are your hosts today. What we have today is we have a movie, which is a movie with a title called Thinking Machines, and the movie is actually not a movie in the classical sense, but it's an interview that is between, it's an interview with one of the pioneers of AI, which I believe is Vannevar Bush, which was later the president of MIT, and David Wayne. David Wayne is an actor, and he was playing the person who does the interview. He's actually a rather good actor. I looked in Wikipedia what he has done. He has won 2 Tony Awards, and he's the male actor who has appeared in most films with Marilyn Monroe. So that's his distinctions about David Wayne that you will see in the movie. So the idea is that when I first saw this movie, I found a colleague showed it to me. It comes from the MIT archives. And a colleague showed it to me, and then I looked at it, and I realized that many of the questions that we have today about thinking machines, artificial intelligence, and questions whether machines will overtake everything, or whether machines can play theater, or are machines creative? All these questions existed back in 1964. So I hope you will agree with me after you see this interview. And then the question was, what has changed between 1964 and today? What has happened in between? So I was very happy that Giacomo, who is one of the key researchers in the University of Zurich and in Switzerland in general, who's interested in neuromorphic computing, AI, will agree to join me. And so after the movie, we would like to have a discussion, possibly on some of the topics of the movie, and of course your input and questions are most welcome. Okay, I hope you enjoyed the movie, and I guess I made a mistake by saying Vannevar Bush. He was Jerome Wisner, and he was actually later a president of MIT as well. Looking back at this movie, we get a little bit of the history of artificial intelligence, of what has happened over the past few years. Of course, this was 1964, so maybe do you want to bring us with the speed you like up to date?
Well, first I'd like to point out the 60s were the most really exciting, but if already in the 40s, McCulloch and Pitts, first from Chicago and then in MIT, actually hired by Wisner, started looking at intelligence. And it's interesting to see from the very early stages of building artificial intelligence systems that there's always been this link between neuroscience, you heard it also, and engineering and electronics and computer science. And McCulloch and Pitts, who were the first ones to invent the artificial neural networks, were a neuroscientist. McCulloch was an older researcher, and Pitts was a young mathematician really interested in Boolean logic and understanding how brains could do logic computations. And actually, they got together because Letvin, who we saw there, was a colleague of both and got them together. And Letvin, McCulloch, and Pitts and Matsurama wrote this paper, What the Frog's Eye Tells the Frog's Brain. And really, it was a really exciting time in which people were trying to understand how brains compute and how to build those with electronic systems. And at this time, in the 60s or in the 40s and 50s, it was very engineering. So people were building intelligent machines by putting the intelligence in it. All the programmers that you saw were actually making some procedural code to tell the computer how to react to the stimuli and what path to follow depending on the state and on the input. So it's a finite state machine, which exhibits intelligence, but as they were saying, it's really programmed. Only in 57, Rumelhart showed or proposed an algorithm for automatically finding the way to classify and distinguish one pattern from another. This was the learning. This was the first instance of artificial learning. And that had a huge impact. And again, in the 60s, it was brought up. And all the way through the 70s with Widrow and Rumelhart in the 80s, the idea of putting together units and allowing them to interact and to respond to stimuli in a way to produce some behavior was really exciting. In the end, standard engineering techniques took over because computers were not very powerful. So there was this winter of the neural networks in the 80s and 90s. And only recently, you probably know, there is this revolution that's happening because of how the power of neural network now is coming out, because there is enough computational power to actually get them to shine. And also the other thing that's present today that was not present before is that there is a huge amount of data and data sets that can be used to train neural networks. So now we're seeing this, this flourishing of neural networks and intelligent thinking machines because we have more computational power, because we have a lot of data, and again, we can put these things together and produce algorithms that really behave as if they were intelligent. But I want to argue that they are not intelligent. It's like some glorified search machines that just search for the optimal solution given a problem, whether you want an algorithm to recognize pictures of cats versus dogs, or to produce some chess moves or Go moves. It's still very much driven by the intelligence of the programmer and the rules that are put in this very constrained condition, like, for example, the Go game. In order to really have emergence of intelligence, there is a school of thought that argues that you need a body. It's not just the theoretical, conceptual algorithm, but also having something that can interact with the environment and produce behavior. That's our the goal of our brain is really to produce behavior. And in order to do that, you need both the body and the environment, and then the intelligence. And I think only with those ingredients, you can really have emergence of creativity and, you know, what we think is intelligence.
Yeah. So there was a discussion about the first industrial revolution and the second, and this being the second. Maybe we are here on a continuation of the second. So the idea was that in the first industrial revolution, you produced machines that they could relieve man from a lot of manual labor. They could lift things higher. There could be heavier things. And what happens now with these new machines, in a sense, someone said actually that what these artificial intelligence machines can do today is only what people can do very, very fast. For example, pattern recognition, to look at something, this is something that we can do very, very fast. And the machine does it also, but when there is something where we need to do significant thinking and significant processes that we don't even understand, it's not clear whether these machine learning or all these thinking machines, etc., are able to compete with humans. So I don't know what are your views about that.
No,
whether
I agree
this is obviously a pro-human view here, but yeah.
No, I agree completely. So the term computer was, before the real computers were existing, was actually a human being. There were these rooms filled with human beings doing calculations for the companies to balance accounts. And so the computer, the first thing that was used for, it was doing spreadsheets for balancing accounts more quickly than humans. And now the same is happening with the deep networks and convolutional networks, these new algorithms. If you go to industries, they are applying these algorithms, for example, for finding defects in material, in textures or stones or even chips. Before, it used to be humans that would really analyze everything, and it would, you know, it would be a very expensive job in terms of salary and time. But now there's these fast cameras and fast computers doing it. But again, it's pattern recognition, like you say, but it doesn't require creative thinking. It's more labor that just looking for patterns.
So if we look at the terminology, is it that we call everything that humans do as intelligent, and everything that resembles what humans do is in turn intelligence? Is this the problem that we have? Is it a problem of terminology? Here is something that humans do, a computer can do it as well. Humans are intelligent, therefore the computers are intelligent too. Or is there something more? You think that the computers can do something creative or is something unexpected?
So this is coming also with the term cognitive. When you talk about cognitive agents or cognitive robots, what is this? And there's been a lot of, I've been participating in conferences where there's very big debates on what is cognition. So it's similar to what is intelligence. And one nice definition of a cognitive agent, so an artificial agent, is something that can react to sensory stimuli, to external inputs, depending on its internal state, and then make decisions based on this. So that it would be an autonomous decision, because depending on the noisy inputs and the noisy internal states, in case of a physical robot or a machine, the outcome is not predictable. And so if something is making decisions based on this combination of factors, then it's defined as cognitive. So in that case, it might be that there is something that is human-like, and it's not just a procedural code of just looking for patterns and saying yes or no. Yeah. So this is active research. It's an active area of research, and I don't have an answer to whether.
So another thing which I found quite interesting, I liked very much, at least it was interesting that there's a lot of Swiss participants in this movie. I like the part with Tinguely, and so there are some machines that supposedly Tinguely made that they produce nothing. And then there's these other machines that they can do pattern recognition or try to lift luggage or to do all these different things. So from an engineer's perspective, one set of machines, they have an objective, and then you reverse engineer what should the machine movements should be to achieve this objective. And the machines that Tinguely was making, there was not really an objective, but it was just putting parts together, and then they were creating certain types of actions. But can you avoid the scenario that if we have an automated way, that we have, let's say, many Tinguelys working together in over 100 years, that eventually they will put something together that maybe will start to do some kind of purposeful behavior and maybe even try to produce machines itself? Can you just create intelligence out of emergence without purpose? Is that a possibility?
It's difficult to answer. You need to have something that has a motivation. So we have our own internal motivations to succeed in life, well, to eat when we're hungry, but even this longer term to succeed in life. So if you could have an agent, an algorithm with some way to interact with the environment that has internal motivations, maybe then through some genetic or evolutionary algorithm or search algorithms will stumble onto something that then will allow him to achieve its goals. But it does need to have its internal motivation. That's why I was saying it's important to have a body. If there is a robot that is running out of energy and realizes that it's running out of energy and then says, I need to find a source of energy, that would be a really internal drive to act on something, maybe overriding the program that says, keep on doing your business. So it might be that in the future, but it would require, one important ingredient would be this internal motivation, which is probably driven by the needs of the body of the agent. Mm-hmm. So,
another thing about the term learning, so at least for as far as I am concerned, at least a lot of the machine learning algorithms, the mathematical expression of that is that you define something which is called an objective function. Mm-hmm. An objective function is that you have the output of a system and you have data for a particular quantity. You look at the difference between the output of the system and the particular data. You create a square around this distance. Then you do a minimization. You follow certain optimization techniques, and you try to modify the parameters of the system so that you match the data. Okay, yes. So to a large extent, classification problems, neural networks, this Rumelhart algorithm is about that. Yeah. I have some parameters and I have an output and I try to match data with the output. So this is what people call learning. But is that how humans learn? Do we learn always with trial and error? Yes, maybe to write letters, we do learn that. We do imitation is a particular thing, but I think, I don't know, what is your feeling? Are there other ways that you think humans are learning? I have my opinion, but I'd like to
Yeah,
hear
well,
what's your opinion.
First, let me tell you and tell everybody an anecdote about this learning. So you mentioned trying to minimize the error with the desired output and the output of the algorithm using minimizing the square. So that's called the delta rule. It was proposed as an iterative procedure in a learning machine. It was first proposed by Bernard Widrow and Hopf, his student, in 65, I believe. And Widrow was at Stanford also in 92. And as a student, I was just going around the various universities. So I asked Bernard, what about this problem of finding the global minimum? Because it's a problem if you have this energy landscape and you go down the valleys, you typically end up in a local minimum, which is not the optimal solution. So I was trying to show that I knew about these things. And I said, well, you know, how can you solve this problem of the optimal minimum, which is very, very hard to solve, and no one has solved it yet. And Bernard Widrow said, with his secretary next, he said, it's not a problem, don't worry. Everybody's married to a local minimum, and everybody's perfectly happy. And the secretary would say, Professor Widrow. So that was just the anecdote about the learning and minimizing energy functions. And our brains actually do that, yes. We have evidence from neuroscience that if you express the parameter, the state space of the neural network as an energy landscape, in the end, the process of changing the parameters of the network actually ends up finding this minimum. So that's one way of learning. But there are actually many other ways of learning. There's many spatial scales and temporal scales in the brain in which learning happens. So there's reinforcement learning, the learning that happens when you do a long sequence of actions and then you get a reward. That then backpropagates or triggers basically changes in all of the parameters that led to that reward. That's reinforcement learning, and it can be on very long time scales. If you study to do an exam and then you get a good vote and then you get a good job, that requires long-term planning and a lot of resources to actually do that. Then there is unsupervised learning, which is only just receiving data and rearranging the parameters of your network so that you can match the data and well represent the data that you get. That's also another type of learning. But the nervous system has all these mechanisms, and the standard engineering approaches actually coincide or match very well what evolution has done with nervous systems.
So as you said, in all this learning, there is the standard learning where you have data and an output. Okay, this is the neural nets.
Yeah.
There's the reinforcement learning, which is the Pavlovian learning, that you have a reward, and then based on the reward, you choose some action, and then you have this classification where you basically separate black pieces from white pieces, and you can do that. But on the other hand, humans, for example, people who learn to be writers, or humans who read to do a theatrical plays or to write books or things like that, one thing that distinguishes humans is this thing called imagination, which I don't know if you can classify it as a learning process, but imagination is about the process by which you create things that don't really exist in front of us, right? I'm reading this book called Homo Sapiens by Harari, and he talks like the first time that humans actually went out of this primitive life is when they started to imagine creatures that did not exist. They started thinking about gods, they started thinking about spirits, and then they started to create stories, and then the stories created communities. And that's it's kind of like the history of humanity. And I don't see, I mean, all the machine learning things, they need either a reward or they need to have some structure in the data that they detect, or they need data. And humans, when we learn or when we create, we don't necessarily have any of these ways. And I don't see how machines can either be doing imagination. I don't see how machines can create causality. I don't see how machines can have all these different traits. I'm not putting them down. I'm just trying to differentiate. So I would like to hear your opinion about that.
Well, on one hand, you can program a machine to create. For example, now there's very nice examples of algorithms that can produce Van Gogh-like paintings or produce music that's very pleasurable to listen to. But again, this has been programmed in. So one can put random number generators and evaluate the fitness of how good, how pleasant is the sound or a picture that comes out based on rules that have been programmed in by the humans. So on one hand, it's possible to program algorithms to create and eventually to produce pleasant works of art, even you could say. On the other, as I was saying before, in order to have something that autonomously decides to explore creative processes, requires really internal motivation. So it does require a body. There is also a neurosurgeon in Los Angeles, Damasio, that wrote the Descartes' hypothesis, which argues that you need, in order to even have feelings, you need to have a body. You need to feel hunger. You need to feel pressure, pain, and that is one of the ingredients that's necessary to have this creative process. So I believe that is true, and that's why I believe machines will not succeed as well as we do in creative. And they're very limited unless the programmer already has some ideas of whether it's going to be a classical piece of music or another piece of music. Those creative processes are very limited, so they're just programmed in by the human.
Maybe I would like to open this discussion to the audience. Maybe there are people who would like to jump in and say one thing or another, if you feel like it.
I'm from the art sector, and I think it's very interesting what you're saying. I just wanted to add that in the 60s there was an artist called Michael Knoll who actually did an experiment with Mondrian paintings. So he basically took one Mondrian painting and made variations with artificial intelligence, and they showed it to an audience, and at the end the artificial intelligence was the winner, like the best painting. So and they even created like a formula for aesthetics. I don't remember the name. I think it was Herkoff's formula or something. So I actually believe that machines can be quite creative. And actually now there's also some exhibitions and artists that really explore this field. So we'll see whether we will maybe also change our taste, that humans start to like this kind of aesthetics. Mm-hmm. It's just a comment.
But for this Mondrian machine, in a sense, I mean, the computer was trained to produce something like Mondrian, right? Or not?
Elements that the computer could use. I mean, Mondrian is obviously a very simple, test. Because you have, it's geometric. You have 3 or 4 different colors, and so you use these elements to compose, a new painting. So it's not a very difficult piece, but recently they did this Rembrandt project where they analyzed 300 Rembrandts. IBM was, I think, doing that research, and the machine created a new Rembrandt, which was completely new. Of course, there were all kinds of elements from previous Rembrandts, but I mean, it's it's probably a question whether it's really creative because it's in the style of Rembrandt, so it's nothing new. But still, it's quite interesting what's possible.
Mm-hmm. Yeah. Also, there are in these deep networks or convolutional networks algorithms where they show and they train the network to distinguish between different artists, Van Gogh and Rembrandt and Monet. Then, if you go and try to analyze what's happening inside the neural network, you just see you will find hallucinations with pieces of different artists, and you can even then have something that is merging between them. So in the end, these internal representations that the neural network comes up with actually are quite also nice and pleasant to see. But again, they've been provided with all the data that Van Gogh created, so the creative process came from the other artists, and then they are combining the various pieces together.
So another application is that also they're using these neural networks, etc., to try to check authenticity of different paintings. And if you have, because it's usually a human being that looks at something and says this is a Modigliani or a Mondrian or whatever, but now you can have computers who do that. So also this brings me to another aspect that so we said there is this aspect of that are today that there are better computers and there is more data and there's probably better algorithms, but there is also another huge thing is that there is a huge economic incentive, that there are a lot of companies that are starting to make a lot of money, Google or Microsoft, IBM, all these companies, even Migros and Coop are making money through these algorithms, and this has created a new incentive to go back and do more research and to produce more for that. So these economic factors and the commercial applications of machine learning have been unexplored before, and that has given also a lot of attention to that today. Yeah, there's back there first, I think. Yeah, sorry, after that.
My question is a little bit, actually it's more to hear your point of view following what you just mentioned before we started the question session, which is, you mentioned that in order to pair machines or computers with human beings, part of the problem is finding a way of building up the intrinsic motivation that the machine needs to have. And also within the interaction, you alluded to the interaction to its environment. So does it feel, does it's hungry or thirsty? But to what extent it is about a threshold of the complexity of the algorithm? So is there a threshold at which there is emergence of this conscience? Because feeling or having a motivation is based on what we feel, what we receive. So this can come from the sensors of we as humans. We have sensors, we have needs, and that determines our motivations to think, to be creative, etc., to survive. Now, to what extent conscience is restricted to a biological substrate, to what extent it is about a level of complexity of a machine before we can see emergence of conscience. And by conscience, I sort of think that is associated to motivations, because you are conscious about your needs, and the machine might have some needs after it. When you reach this threshold of complexity, where you see emergence of this conscience. So can you comment, both of you, about what is your understanding of to what extent a machine can reach the state of consciousness, and to what extent that would lead the machine or close the gap between the machine and the human being in that being conscient basically dictates or alludes to implicit motivation and feelings and needs.
Yeah. So my advisor was Christoph Koch, who's one of the world leading experts in consciousness, and the term consciousness is already that, even when we're talking about consciousness in human beings, is ill-defined. So I don't know if what you have in mind is self-awareness, when something becomes aware of the self, then and that is a threshold. So now there is a term they're using also for the point in which machines will become self-aware. It's called the singularity, and there are people that are arguing it's very dangerous, and there are people that are arguing, oh, it's no problem. So it's very difficult to say when this will happen, if it will happen at all, if we will have artificial algorithms that will become self-aware. But I think that the motivation is a necessary condition, it's a necessary ingredient. And when that is there, then, of course, you need to have something that interacts with the environment. You need to have sensory input so that this agent, this artificial machine, will be able to realize whether a part of its body belongs to the machine or belongs to the outside world. But before I think we get to that point, there's going to be many, many years of research. I don't think we are risking of creating an artificial machine or an artificial robot that can become self-aware and conscious in any time soon. There's so many problems. And it's not really the technology. The technology, we have the tools and the potential, the transistors to put millions and millions and billions of transistors just like the human brain has 10 to the 11 neurons. It's really the understanding. Once you put together these building blocks, how do you connect them together, and what are the rules that allow these dynamical systems to interact in a way to have emergence of consciousness? So that's really theoretical and basic research that we need to do, and neuroscience. We need to look at existing systems that have this self-awareness to understand how to do that. That's my.
So from my point of view, I think that maybe it's a matter of vocabulary again, because what we call consciousness from a human level is something that we understand as humans, the feelings, the motivations, all these are things that are maybe characterize us. And now one question about the consciousness is when you have a machine and you observe all the sensory inputs, you can observe all the outputs, you can observe the computer program. If you can observe everything, this is something that you can do to a machine. But to a human being, I think the way we process the sensory inputs, it's not probably something that we totally control or we totally understand. A way that we may react today may be related to something that happened to us in our childhood. And something triggers it today, and the two things are being combined. And that's the particular complexity of humans, of the way we have built, the way our neurons are working. So I think if we understand how the brain works, how all these symbols that are coming from the past are affecting us in how we decide or what we do today, if we understand how the brain works, then maybe we can eventually build machines that would have some consciousness that would be similar to us. At the moment, I see as the main difference that for everything that we build, we can observe everything and we can know everything. With humans, you cannot exactly know the causes why someone does something irrational or rational. We also very often, humans, we are also not very good at rational way of doing things. We are very irrational in how we decide, how we choose, how we do things. If you have a computer, computers are usually very rational. And so I'm not sure the two consciousness would ever be together unless we fully understand the brain, and then we can build machines like that.
Just a comment, a sort of film about AlphaGo, and there was a point where the engineers who were assessing the movements of the machine, of the algorithm, came to a point where the machine was creating moves that appear to be really creative. So, and also in relation to the allusion to the machine being self-aware. I mean, people who meditate realize that there is no self, right?
Yeah.
So consciousness might be separate from the self. So in that regard, the path of towards consciousness for a machine might not come from the self. And I also agree with you with the fact that, I mean, we cannot rationalize our behavior. To some extent, we tend to think that we might rationalize the behavior or the outputs of a computer, of an algorithm. But do we really know and can rationalize the outputs of a machine? I mean, I heard that machine learning people might develop the algorithm, but they might not understand the outputs. And the uses of those algorithms, machine learning-based algorithms, is that the outputs are the good ones. So we're pleased with the outputs, but we might not understand how the machine came up or selected those outputs.
Sure, this is the explainable artificial intelligence. That's the big thing to understand, because the next thing you want to do is you want to understand because you want to trust, you want to have faith. If a machine tells you take this pill today or cross the street, you want to know how they decided this thing. But just because something has an output, it doesn't mean that it has any necessarily, output does not mean necessarily causality or intelligence. But maybe we can, you still want to have your question, or you wanted to raise something, or I think he was first. Okay. All right, yeah.
I'm sorry. Yeah, I have a question. What's your take on how algorithms can be beneficial for the democratic process? We have seen, of course, the Cambridge Analytics 1.5 year ago, 2 years ago, and that was basically perceived as a kind of negative example of how algorithms steer or influence the democratic process. But what do you see of potential for collaborative choice making, and also choice making of, let's say, ordinary people far away from, let's say, the technology of algorithms?
So again, we're using technology, and that is something that's basically driven by human beings. So even when people are building mechanical equipment or arms or electronic algorithms, it's always the same problem. If people decide to use it in deviated ways, then it's going to be a problem. So the potential of the technologies is very high. So it can help the democratic process. It can really bring to everyone the ease of choice, ease of selecting and voting. But the dangers are also very high, because it can be hacked, and so it really requires a lot of work on the security aspects, which is not trivial. So, but also good faith in the people that want to use it, and in the technicians that are behind it, that actually build this. So it really requires a strict control process from the very beginning, to the first programmer that does the very simplest part of it, to the last one, the person that actually installs the machine in the end. And then in making sure that it's protected from the internet and secured. So the security part, I think, is a big part of it that should be not under-evaluated, or because it really requires control from the first steps to the very last.
And one of the things with this Cambridge Analytics, if you see the democracy in which it was first applied, it was the United States. It was not Switzerland. And I don't want to say that the democracy of Switzerland is better than the democracy of the United States, because we enter into dangerous territories. But what is interesting, for example, in Switzerland, whenever people are voting about something, you see a lot of discussion. You see the pros and cons. I don't know how many people are looking necessarily into that, but definitely I would say there is a lot more argumentation, and there is a lot more truth, and then there is a lot, maybe the general public, you would say that they're more educated on the average. So if you go, on the other hand, in the US, it's not necessary. People would look at the internet and they believe things more easily because the culture is like that. There's not necessarily a lot of debate. So maybe in these countries, it's easier to manipulate. So the answer to all these things, it's the same thing as it used to be in the past. The people that they were versed in reading and writing, they had an advantage in the society. I think what you need to have now is you need to have people who know how to program, who know what is an algorithm, who know what you can do with an algorithm. So I think, I am possibly biased, but I think programming or algorithm thinking, or what algorithms can do, starts to become as important as reading and writing was in the past, okay? By reading and writing, it doesn't necessarily mean that you will choose the right candidate or you will have the right choice in your democracy, but at least you are more responsible on the choices that you are making. And I think that's the best that we can hope from people, that they make the best of the choices based on their individual interests. That's perhaps what democracy is, an agglomeration of individual interests. It's a very interesting topic. Of course, there are dangers. Of course, the more you switch off your brain and you accept everything which is in front of your screen as the truth, the more susceptible you are to any kind of manipulation. So we have to be aware of that.
I'm just wondering whether we are here dealing with a kind of a language, actually, with this artificial intelligence, because basically it's influenced, as far as I understand, it's by the people programming it, so it's their minds, their intentions. As an example, like this now, social profiling in China, this is going to be forced upon the people and will be endemic, and it will reach us, whether we want it or not, as well. So we all will deal with that one day. But then this has been programmed with an intention to control the people there. So it's like a kind of a political way of thinking that is programmed in there. At the same time, there's these cryonics people who actually want to download the knowledge or consciousness of a person and preserve it, just in case it should be possible to actually give it back to another living creature. So now, if these two developments actually intersect one day, I'm just wondering whether there could be possibly a moment where this consciousness, which seems to be detached from the body then, could actually start to evolve somehow.
I mean, if I can go back to your thing that you said in China, it's not only in China that they do it. I mean, when you apply for a loan, right? I mean, the bank, usually they know a lot of things about you. Also, the supermarkets know a lot of things about us when we go and buy whatever we buy. So there's a lot of people actually that slowly know more and more things about that. And again, the only resistance that I can think of that is education, to be able to go back and say, I don't want this, or I want to have legislation against this. I don't agree with you that one day we will be like China, we want it or not. I think our history, our culture are different. I think we can possibly resist in a different way. But that's a longer thing. But yes, there are indeed dangers of totalitarian situations where indeed people can actually download possibly on you a particular conscious or a particular image of the world. And in a sense, this is happening when you see all this fake news or all the different things that are being projected on us from different channels. But we still have choices. And it's a choice whether we have a TV or whether we spend 20 hours a day looking at the news, or whether we read. Yes, it is. It becomes, there is a lot. It's a very interesting question. I mean, it starts to go that they have found ways of giving us little pleasures. Someone was telling me that every time that you see a like in something you posted, you get a shot of dopamine in your brain. People have actually seen that. So they make you to be addicted to this by basically taking these pleasures that you get. Oh, someone likes me. Oh, and I get a like. It doesn't really mean anything that someone liked what you got on the internet, but then you also get trained to go back and look for more of that. And you also participate in that. So somehow this thing is happening, but I think we need to resist. I think by education, by telling people that this is happening, and explaining to people that this is happening, that's maybe one way to resist. So, yeah.
Yeah, the term addictive is the right medical term. It is addictive. It's a medical condition, actually. And even big companies like Facebook and Google are putting in extra tools to warn users whether they are spending too much time on the social media or something. But going back to the artificial intelligence, the artificial intelligence is called like that also because now these algorithms are inspired by the brain. So they use neural networks, they use combinations of units that communicate in a massively parallel way, just like the neurons in our brain. And our brain is extremely plastic. I don't think there's going to be anytime soon a technology that will allow us to download our consciousness or our thoughts. because our synapses, first of all, at least some of us are losing 1 million neurons a day. Some others are having 10,000 new synapses a second. So our brain is changing its shape continuously. And in some cases, it will be changed forever. For example, now I will remember this thing about China for forever, or at least for the next 20 years. In some other cases, the synapses are only lasting a few hours. And so it's going to be really difficult to take a snapshot of, the 10 to the 14 synapses and all the molecular contributions that are there and put it in information and store it somewhere. So that I think it's going to take several years before we get to a point where that can happen.
Please.
Well, you answered already my question a little bit. I have a question about like a little bit different approach how to reach artificial intelligence. Maybe you know the Human Brain Project in Lausanne at EPFL, where you try to connect a lot of devices like neurons in our brain to model the brain. Do you know that kind of or could work in a way, or is it more than is a human brain more than that?
Well, yes, we are involved in the community. So I'm one of the advisory boards of the Human Brain Project, one of the members, so I know them very well. So there are several aspects. One is using supercomputers to simulate human brains. One is using technology, microelectronics, to build human brains. And the other is the neuroscience, actually looking at real brains and then trying to extract information. So it's a very large project that's trying to tackle this problem. But again, the field of neuroscience is still at the very early stages. Before we get any understanding of the whole system, it's going to take many, many years. We know a lot, I mean, the community, not just we, the neuroscience community has learned a lot, especially from the 60s to now, on how the sensory, the peripheral part of the brain works, the retina, the cochlea, the sensory periphery, the somatosensory. We know how we make decisions. We know how we control our muscles, and from the motor cortex, how we can, learn to play piano. We even know how we can plan long-term. In the frontal cortex areas, there is the long-term planning where you can say, if I want to get a good job, I need to study and pass exams. But putting everything together and understanding how all these distributed modules interact, it's still an open challenge. It's still unclear. And the Human Brain Project is making good progress in trying to tackle parts of it, but it's only very small parts that we are trying to put together.
So maybe a last question. We have to be out of here by 8, as I understood.
In this film, we saw a child who was deciding which glass was full with milk. And in my experiences, when children learn, at some stage, they say no, very decisively no. So in my opinion, it's a signature of intelligence that you know when you have to say no. Do you know of any algorithm or robot who has reportedly said no to its task, which was given to him?
There's a quick answer is the HAL in the 2001 Space Odyssey, but that's a movie. But I don't know actually myself. I don't know.
I also don't know of any of such examples. Unless it was a bug, like the ones we saw. Yes.
It could be the victory of the Eine, if they say no in one point of the time.
It could be. Yeah, this singularity, this moment in which the algorithm becomes self-aware and says, no, I'm not going to.
I don't want to learn anymore, right? Yeah. So I think I'd like to close. I'd like to thank everybody for sharing the evening, and I wish you a good continuation and a good evening. Yeah.